So hi everyone, today we'll be discussing on what are ensemble models in machine learning. So basically, first of all, we will be starting with one of the concept of decision tree. So decision tree has been one of the most commonly known models, and I think if you have in the data science space for some time, you must have heard of the concept of decision tree. So I won't be going into that. Now the major point why I'm talking about decision trees because it is also considered as weak learners. So what are weak learners? Weak learners are taken as the models who are performing just better than random guessing, so their performance is better than 50% of the accuracy, you can take in that sense. So now coming the idea of ensemble learning. So ensemble learning is nothing but aggregation of a number of weak learners. So now weak learners can be decision trees, for example, which are most commonly used. Now what we would be doing is that we would be taking multiple decision trees. We would be aggregating their results in multiple ways, so it won't be that we would be considering an average and just going with that sense. So there will be multiple techniques that we will be using to aggregate these results, and the final result would be a result of the ensemble that we have generated. So let's get started. Let's first discuss about random forest. So random forest is something that I am assuming you all must have used. So random forest is based on the idea of bagging. So in bagging, what we are doing actually is that we are considering number of n number of decision trees, and then that are independent of each other, so they are not related to each other. The next part that we are doing is we are considering the whole data set, sampling the data set into different batches, and also we are not providing all the features to all the decision trees. So it can be the case that a data set is of the size 2000 cross 10 features. So to one of the trees, and we have five decision trees, for example, in the aggregation. So we are feeding one tree with three columns, 100 samples. The other tree we are feeding with five columns with 1000 samples. The other tree we are feeding with all the columns with just 200 samples. So in this way we are subsampling the data set quite randomly, and then feeding it to different decision trees. Now eventually the final output is dependent upon once these models are trained. While testing, what we are doing is that we're feeding a test data set, and then the output that we're getting from all the trees, we're averaging that, and then finally using it as the final output. Next, moving on to gradient boosting machine. So, as random forest was based on the idea of bagging, gradient boosting machine is based on the idea of boosting. So, in boosting also we are again aggregating multiple trees, but with a difference. So, in case of random forest, the decision trees are independent of each other, but in case of gradient boosting machine, it is not. These trees are working in a sequence. So, for example, what happens is ki, assume that we have 1000 training samples. We feed it to the first tree, that is F1. Therefore, it takes a training data set and produces an output y1. Right. Now the next tree, that is h1, will intake x as an input. The input remains the same for both the trees, but now the prediction it has to do is y minus y1. Y is a true label. So making sense. The second tree is trying to improve over the errors made by the first tree. Right. Similarly, if there are more trees, the sequence continues. So eventually, this is the whole idea of boosting. In gradient boosting, this is what we are doing, where we are considering multiple trees in a sequence, where the tree coming next in the sequence is trying to improve over the errors made by the previous trees. Now coming to the most popular algorithm, XGBoost, which is a king in Kaggle competition, and it has also been believed that it is one of the it can even outperform neural networks over tabular data sets. So what they are, XGBoost is also an upgraded version of GBMs only, boosting machines, but they are way faster and uses less space. Basically, the whole ideology of XGBoost, the major improvement that has been done is they're trying to figure out 100 like they're trying to figure out n best possible breakpoints. So in decision trees, you know that we are having splits happening. So if thousands of splits are present for a decision tree, they would be considering the 10 most or 100 most best splits that are possible using an algorithm called as pre-sorted splitting algorithm. I won't be deep diving into that algorithm. It is also called as a regularized GBM because in boosting, as we saw in the previous version, we were using the models in a sequence. So in this case, in case of XGBM, what we will doing, we will be also providing a discount factor or an alpha getting multiplied with the results of the next stream can be taken as a weight also. So instead of the prediction considering as h1, the secondary that you remember from GBM video, we will be considering L into h1. L is a constant. Coming to light GBM. So light GBM is again an upgrade over GBMs only, and they are also quite similar in terms of performance to XGB boost. So the only difference between the two algorithms, the rough difference with the two algorithms is the way they're choosing over the best split. So they are also based on the idea of choosing the minimum, the best splits rather than all the splits, saving on time and space. So as in case of XGBoost, I told you that we are using a pre-sorted splitting algorithm. Gradient boosting uses LGBM uses gradient based one-sided sampling algorithm. So the way they're choosing their splits in a particular tree is using different algorithms, and hence they are different in nature, though their performance is quite similar, and you can exchangeably use XGBoost or LGBoost. The performance should be quite close. The last, not the least, is CatBoost. So CatBoost is comparatively slower than both LGBM and XGBM, but it is giving you a very great advantage that it can handle categorical data directly. Right. So there is no need for you to convert this data set into one-hot encoding or label encoding, but the data set can be fed directly to the model. Hence, it understands categorical data, while other models are incorporating data set as considering this category as numerical feature. Hence, that is why we require conversion. So that is the advantage that CatBoost provides. So in this video, we have discussed about five major ensemble modeling algorithms, and they all have their advantages. One of the most used class of models, which gives you great results compared to other classification or regression models. Yeah.